to all of you. Good morning to another session. I welcome you to yet another session on interference. This is the second part of interference. We started interference on the last lecture and we have covered a significant portion of it. By today itself, we'll try to complete this interference, and after that we'll go for diffraction. So before I start, let me know if everything is all right so that we can start. Can you hear me properly? Can you see me properly? Audio, video, everything is all right? So this is lecture number 42. So this is lecture number. Okay, I think everything is all right. Without any further ado, let's start. On the last class, we talked about Young's double slit experiment. Today, we'll start with triple slit experiment. So if instead of 2 slits, if there are 3 slits, what kind of interference pattern we'll get? So this is going to be very interesting. Intensity of 3 slit interference. So as from the name, as far as the name is concerned, we can understand that there are 3 slits. Okay. So previously this was the thing. 1 slit. Okay, 2 slits. And another slit will be there. Three slits. And as usual, we have a screen here placed, let's say, at a distance d. This distance is d, and you see the separation between the slits, consecutive slits, is d. The center to center distance between these 2 slits are d and d, so the overall distance becomes 2d, right? So instead of 2 sources, here we have 3 sources. One is S1, another one is S2, another one is S3. So because of these 3 sources, we are investigating or observing a point, let's say P. How the intensity varies here because of the interference. Good morning, Ajay. So what will happen? Let's say a light ray will go from S1 and will give its disturbance. Light ray from S2 will go, and another light will go from S3. Okay. Now, let's say this angle we are denoting the mid slit, and this angle we are taking, let's say, theta. This angle is theta. So this is the overall scenario. This is d as usual. Now to satisfy the condition of interference, the sources must be coherent. So we are going to take that, and all of these waves are having same frequency. And as you can see, the path traveled by the light emerging from S1 will be different from that of S2 and that of S3. Okay. So if you see it, if this is d sin theta, this will be 2d sin theta. Suppose a monochromatic Good morning, Murli. Where is Harry today? Monochromatic coherent source of light passes through three parallel slits. S1, S2 and S3, each separated by a distance of d, each separated by a distance d from its neighbor. The waves have the same amplitude, let's denote that by E naught, and same angular frequency. Angular frequency omega, but there exists a constant phase difference, because there is a part difference of the part difference between the rays emerging from S1 and S2 is d sin theta, between S2 and S3 is another d sin theta. If you consider the effective part difference between S1 and S3, it will be 2d sin theta, but a constant phase difference, this is delta, is equals to, look, 2 pi by lambda into path difference. Path difference is d. So this is between the neighboring source. So let us now consider, let the three waves emerging from the slits B. How can we write? If I write, let's say, the first wave to be E1 is equals to E0 sin omega t. Okay, so E2, it is having same amplitude and same frequency, but a constant phase difference of delta, so it will be plus delta. And the third one we can write E0 sin same frequency omega t, another delta, so this will become 2 delta. Can you write it? Now if you want to calculate the intensity produced due to the interference, what we have to do? We have to utilize the principle of superposition of light waves. First of all, if we are going to calculate E1 plus E2 plus E3, we need to calculate the combination of E1 and E3. Let's say first we are calculating E1 plus E3, then we will just add it to E2 to get the resultant electric field intensity at point P. So E1 plus E3 is equals to E0, okay, multiplied by sin omega t plus sin omega t plus 2 delta. Can I write it? So now you know a trigonometric formula. What is that formula? Sin C plus sin D. Sin C plus sin D. What is this formula? 2 sin C plus D by 2. Okay. Cos C minus D by 2. This is the formula we know. You have read it in your class 12. So we are going to utilize this formula here. So what it will give you? Alpha is equals to omega t, sorry, C is equals to omega t, D is equals to omega t plus 2 delta. So this will give you 2 E naught sin omega t plus delta times cos delta. Cos of minus theta is equals to plus cos theta, that we know. Once we calculate E1 plus E3, now if you add this, the remaining E2, you can get the resultant electric field at point P. Therefore, the total electric field the point P on the screen is E is equals to E1 plus E2 plus E3. You see, although these light waves going reaching to point P seems to be originated from a very long from unequal distance, but if you imagine the practical case, these slits are separated by a distance which is less than a millimeter. Okay, and the screen is placed at some further distance which is much larger than this separation of the slits. So we can imagine that these light waves are traveling in a same direction, almost in the single direction. That is why we could able to remove the vector signs. So that is there. Okay, we have just mentioned to you E1 plus E2 plus E3. If you do this, so E1 plus E3 we have already calculated, that is 2 E naught sin omega t plus delta cos delta plus E2 is E naught sin omega t plus delta. That is the reason we took E1 and E3 first, because we are getting a common term of sin omega t plus delta. So if you take this common term E0 sin omega t plus delta, you are left with 1 plus 2 cos delta. Delta is equals to 2 pi by lambda into d sin theta. Now, since the intensity is proportional to the square of the electric field, the intensity is proportional to electric field square and average, E square average. Therefore, what we can write? We can write that I is proportional to E0 square into 1 plus 2 cos delta whole square into sin square omega t plus delta. So this part, it does not involve this t factors. So we call it, okay, this is E naught square Acha, we need to take the average. So average will be taken on this variable function, right? Now 1 plus 2 cos delta whole square, this part is constant. 1 plus 2 cos delta whole square constant. Now sin square average, sin square average or cos square average, that produce half. So divided by 2. So if it had cos also, cos square, then it would have also produced half. Sin square omega t plus delta average is equals to half. But if you take sin omega t plus delta average, that will produce 0. Remember this simple thing. The square will produce half if it had square, average of the square. But if you simply take sin omega t plus delta average, then that will give you 0. Now this is the expression of intensity. Okay. Now we can say the maximum intensity. When do you get the maximum intensity? Maximum intensity is obtained obviously for cos delta if you take plus 1. So we can write the maximum intensity look I naught is equals to, if you put cos delta equals to 1, so 1 plus 2, 3, 3 square by 9. 3 square means 9 by 2. 9 E naught square upon 2. This is the maximum intensity, we are denoting it by I naught. And using this, we can write, let's say I, you can see E naught square by 2 is equals to I naught by 9. From here, you can say that E naught square by 2 is equals to I naught by 9. Here you can see E naught square by 2. So we can write I by I naught, or rather I should write it in this way. I is equals to E naught square by 2, that is I naught by 9 into 1 plus 2 cos delta whole square. Can you write it? And this value is equals to I naught by 9 into 1 plus 2 cos delta is equals to how much? 2 pi by lambda into d sin theta whole square. Now if you plot this intensity profile, what kind of graph you will expect? Okay, so we got the maxima at cos delta is equals to plus 1, right? If we plot, let's say cos delta is equals to, if you take cos delta equals to minus 1, if cos delta is equals to, okay, 2 cos delta is there, so we cannot take minus 1 simply, that will not make it 0. If I take it instead of minus 1, if you take it minus half, then this 2 will be cancelled. If cos delta is equals to minus half, the minimum intensity okay, minimum intensity is not always zero intensity. Okay, the minimum intensity is obtained. So here I minimum is equals to 0. Now for cos delta is equals to plus 1, we get the maximum intensity, and for that I by I naught is equals to how much? It is 1, right? So keeping this in these things at mind, we can plot the graph. So we have three things we need to take care. Firstly, maxima and minima, and in addition to this there is another thing. In addition, there are secondary maxima. There are also secondary maxima which are located at you see, if you take cos delta is equals to -1, if we took cos delta equals to -1, we are expecting minimum, but it is not minimum, it has some finite value. Okay, that is not the minima. There are also secondary maxima which are located at cos delta is equals to -1. So if you take cos delta is equals to -1, what is your I? I is equals to I naught by 9. It means I by I naught is equals to 1 by 9. So as you can see, it is 1 by 9th of the original maxima. So this is a primary maxima, these are secondary maxima, and cos delta equals to -half, this corresponds to minima. Okay. Now where should these points exist? Cos delta is equals to -half. Where should this point exist? Delta is equals to, let's say, d sin theta 2 pi by lambda into d sin theta. Cos delta is equals to -1. If I particularly talk about this condition, so this condition implies that delta is equals to how much? 2m plus 1 into pi. So what values of pi? What is the primary and secondary maxima? Primary maxima means the maxima will be of large intensity. Secondary maxima will be 1 by 9th of the primary maxima. We'll show you, because we are getting these conditions. So wherever delta value is like this, m may be 0 plus minus 1 plus minus 2 and so on. So what is delta? Delta is equals to, we can say, 2 pi by lambda into d sin theta. This is equals to twice m plus 1 into pi. Okay. So from this we get d sin theta upon lambda. This is equals to m plus half. And the values of m are given by 0 plus minus 1 plus minus 2 and so on. So let me just show you what kind of graph you get. So we are basically plotting I by I naught versus d sin theta by lambda. Okay, I am plotting it here on the new slide here. So we are basically plotting the intensity pattern obtained in a 3-slit interference. Along x-axis we will be plotting d sin theta by lambda. Along y-axis we will be plotting I by I naught. So at this 0 value, we have I by I naught is equals to how much? 1. We have obtained I by I naught for cos delta is equals to 1. So you can implement this in this way, the way I have shown you here. If you implement cos delta is equals to plus 1, so it is cos twice m pi, right? Now delta is equals to twice m pi. Delta means twice pi by lambda into d sin theta is equals to twice m pi. So from this we can get the value of d sin theta upon lambda. This is equals to 2 pi is cancelled. So m. So wherever you get integer values, so m is equals to 0, plus minus 1, plus minus 2, and so on. Okay, similarly you can also obtain a relation for cos delta is equals to minus of the position of the minima. Okay. So m is equals to 0, plus minus 1, plus minus 2. This is proportional to m, you can see. So at whole value you will get this principal maxima, primary maxima, and this half whole value you will get secondary maxima. So let me just draw the curve first, then you will understand it more clearly. So here you will get a peak, big peak. Here you will get a big peak like this. Okay, so this intensity value will be 1, and here you are getting a minima. Again, here you will be getting a secondary maxima, and this intensity will be 1 by 9. If this is 1, this value will be 1 by 9, and as you can see, this is obtained for, let's say if you put m equals to 0, you will get half. So this value will be 0.5. And again, at a whole value of 1, because it is proportional to, you can see you will now put m equals to 1, d sin theta by lambda is equals to 1. So at this location, what you get? You will get again the primary maxima like this. You will get a primary maxima. Okay, let me just draw it for you. You draw it and make sure that you make the intensity same as the previous one, like this. Like this. Then again there will be a secondary maxima and a primary maxima again, like this. If this is 1, this will be 1.5, this will be 2, and the because it is values for both plus minus values, you can see these things will be repeated on the other side as well. Minus 0.5, minus 1, minus 1.5, this is minus 2. Okay. And it will keep on going. Let's say the proportionality constant is 1 here. Okay. So while calculating this whole thing, that is taken care. I have calculated the average. Actually, look here, we can write I equal to also we can write, because you are not emitting anything. We are just squaring E square. You are not squaring the amplitude only. We are squaring the whole thing. That is why you can imagine that the proportionality constant is 1. So understood the concept of primary maxima and secondary maxima. So this is your primary maximum. And these are your secondary maxima. Everything is all right now, guys. So you got the fundamental difference between a double slit and a triple slit interference pattern, I hope. If anyone has any question, you can ask. If not, then we can go for a problem which came in 2018 June. Harry, Ajay, Muli, everything is all right? Can we move forward to the next slide? Is it done? Let me know when it is done. Let's give it a try to this problem. This came in 2018 June. The following configuration of 3 identical narrow slits are illuminated by a monochromatic light of wavelength lambda, as shown in the figure below. The intensity is measured at an angle theta, where theta is the angle with the incident beam at a large distance from the slit. So at a large distance from the slit, it means that you can take that all the waves are going in the same direction. If delta is equals to 2 pi by lambda into d sin theta, the intensity is proportional to. How you are going to do this problem? Look, the way we calculated using sine or cos, we have taken sine, so we can also take exponential. We have also derived this initially. We can also take the electric field expression in terms of exponential. So from the first slit, if you take E1, let's say a e to the power I omega t. Let's say we are making it a vector in the vector form, but later we'll consider that they are moving from a very large distance, so they will appear to go in the same direction. Now as you can see, E2, what will be E2? E2, they will be having, let's say, same magnitude and same frequency. So it is separated by some distance d. So let's say that is delta. Here you can see the distance is doubled. So what you will take E3? Frequency is same, plus you will take it 3 delta. So do it. It will be easier for you to add the exponential. Calculate E as a sum of them, E1 plus E2 plus E3. Then you can calculate E star because they are complex quantity, and then later you can use the formula of intensity mod E square E star E and check what value you get. Could you do this problem? Let's say, let us take E1 to be A e to the power I omega t. Therefore, E2, the electric field coming out of the second source, will be A e to the power I omega t plus delta, and E3 will be A e to the power I omega t plus, because you can imagine it is 2 delta, so it becomes 3 delta, where it is given that delta is equals to 2 pi by lambda into P sin theta. Therefore, if you consider the resultant electric field produced due to all of these three sources, it will be the sum of E1, E2 and E3. So A is common, okay. So A, and you can imagine it in this way. A e to the power I omega t times e to the power I delta. Can you write it? No issue in writing this. And in a similar manner, we can write a e to the power I omega t. So let's take out the common factor and keep the remaining portion. This is e to the power thrice I delta. So if you take e to the power I omega a e to the power I omega t common, what you get? You get 1 plus e to the power I delta plus e to the power minus 3I delta. Okay. Therefore, E star, this is equals to a e to the power minus I omega t 1 plus e to the power minus I delta plus e to the power minus 3I delta. यहाँ पे प्लस है ना. And that is why the intensity I, which is mod E square E star E. This is equals to A square e to the power I omega t cancelled. So you are left with 1 plus e to the power I delta e to the power 3I delta multiplied by 1 plus e to the power minus I delta plus e to the power minus 3I delta. Now we just need to simplify this expression. What you will get a square into, look, 1 plus e to the power I delta into e to the power minus I delta, another one e to the power thrice I delta e to the power minus thrice I delta, another one. So total 1 plus 1 plus 1, 3 you will get. Plus e to the power I delta you are getting from here, and 1 into e to the power minus I delta. This 2 will come. Now, if you multiply e to the power 3I delta and e to the power minus I delta, you will get e to the power plus twice I delta. And e to the power I delta, e to the power minus 3I delta, you will get plus e to the power minus 2I delta. Again, 1 into e to the power 3I delta into 1, e to the power 3I delta e to the power 3I delta, and here 1 into the power minus 3I delta e to the power minus 3I delta. Now we have taken these terms in this way so that we can make it in this way: divided by 2, multiply by 2, divided by 2, multiply by 2, divided by 2, multiply by 2. So a square times 3 plus, this is cos delta, this is cos 2 delta, this is cos 3 delta, and I think it has matched with one of the options. C. So I is proportional to this thing. Clear? If you have any question, you can ask. Can you move forward? Give it a try. A screen has two slits, as you can see, each of with W with their centers at a distance of 2W apart. This width is W and center to center distance, this is 2W. It is illuminated by a monochromatic plane wave. Monochromatic means having single lambda value, plane wave traveling along the x direction. The intensity of the interference pattern measured at a distant screen at an angle, let's say theta is equals to n lambda by W to the x axis is. Can you do this? Simple problem. If you have the concept, you can do it. If this angle is theta, you know, if one ray goes from here, another ray goes from here, what is the path difference? And as the screen is situated at a very large distance, we can take this theta to be very small. So sin theta can be approximated to tan theta, can be approximated to theta. So sin theta can be approximated to theta. From this, can you do this problem? Little bit tricky problem, but I think you have sufficient concept to solve this problem. We have already discussed. At least after giving you the solution, you will realize. We have done the theory in such a way that if you have understood it properly, you will be able to solve any type of questions. But you may not get the essence in the first time. If you revise maybe 3-4 times, you will get the deep insight. Look, what happens when we are reading it for the first time, when we are learning it for the first time, you will understand eventually everything. But that insight you get from a particular topic, that comes after multiple revisions. Okay, if you revise 2-3 times at least, you will get the insight, and that helps you to tackle this kind of complicated problem. Otherwise, by just learning the things, you will not be able to solve questions. Okay, because in CSIR-NET, your analytical ability is also checked. The things will be solved upon whatever concept you have, but you need to have the art of applying those concepts in the right proportion. Do it, guys. Clarify a question. Could you solve this problem? So let me just give you an explanation for this question. You see, let's say this source is S1, this is S2. Okay. Now, if this two source produces its effect here, you can see let's say this is P. So what is the path difference? Do you know this one thing? For the double slit, for the double slit interference, path difference delta is equals to n lambda. This is the condition for bright fringe. Bright fringe or maxima. And when we have delta is equals to the odd half integers n plus half lambda, this is the condition for dark fringe or minima. This one you know, no issue in this. So for bright fringe, what should be the path difference? The path difference will be lambda, 2 lambda, 3 lambda, 4 lambda. For dark fringe, the path difference will be lambda by 2, 3 lambda by 2, 5 lambda by 2, and so on. Now for the present case, as you can see, the path difference between the two rays, the path difference between the two rays, between the rays, let's say one is S1P, another one is S2P, is delta X, let's say. Delta X S2P minus S1P. This is equals to, we know this formula very well, d sin theta, because d is what? D is the distance between the two slits, center to center distance. Okay, this much is d. As you can clearly see in this question, d is what? 2w, right? Because each is having a width w, and from the figure you can see that d is nothing but 2w. It has mentioned also their centers are a distance of 2w apart. D is the distance between the slits. What separation? So now in the given question, d is equals to 2 times w. Therefore, we can say that delta x is equals to 2w sin theta. Now, as the screen is situated at a large distance, we can imagine that this theta value is very small. Since P is situated on a distant screen, if I consider this to be d, so d is much greater than small d. Sin theta is very small. And hence we can approximate sin theta to be equal to theta. and as a result your delta x value becomes 2w theta. Now you have to find out at this angle theta is equals to n lambda by w. Okay, theta value you are given. So intensity of the interference pattern. So what will be the intensity at this angle theta? So we'll put the value of theta here. At an angle theta is equals to n lambda by w, we have delta x is equals to 2w multiplied by n lambda by w. So this is 2n lambda. What is this condition? You can see it is matching with the condition of bright field. So this is the condition of maxima, n value being 0, 1, 2, 3. So which option is it matching with? Okay, now if you take a 0, then that will make it minima. Okay. Yeah, we can also take 0, but to match it with the options, we can say maxima for n equals to 1, 2, 3 and so on. Option B. Clear this question? I have tried to make it as detailed as possible for you. Let me know once it is done. We'll go for the thin film interference involving multiple reflections. Quickly guys, is it done? Okay, now look at this very interesting phenomena, interference involving multiple reflections. So when a thin film of some transparent material is exposed to light, circular patterns of brilliant colors can be seen. For example, colors seen on a soap bubble, or formation of colored rings on a wet road on which car oil has been spilled. This is due to the interference of light reflected from the upper and lower surface of the film by a method of division of amplitude. This one is very important. We have made you understand what is the meaning of division of wavefront and division of amplitude. Young's double slit experiment, here we are making use of the division of wavefront. Okay, wavefronts is getting divided, but here we are making use of the division of amplitude. So some intensity light is coming and its intensity is getting divided by reflections. You can see one part of it is reflected directly and another part is entering or refracted. This is the thin film. Here film exists. It may be air film, oil film, whatever material is there. So here it is air, here it is film, this is air. Okay, so you can see one light is coming, it is part of it is getting reflected and part of it is refracted, and this is involving multiple reflection within it, and so it is also emitted and some portion of it is also transmitted. Okay, so it is making use of the division of amplitude. The initial amplitude is divided into different components. And because it is involving multiple reflections, you will get a pattern like this. And this is a practical example. If you spill a thin layer of oil on the road, you will get this kind of colorful fringes. This is because of this multiple reflections. Now for your CSIR-NET exam purpose, we need to know few things. We need to know the conditions of getting interference pattern. Okay, so first of all, this is based on a division of amplitude. Remember this thing, division of amplitude. How amplitude is being divided? Let me just draw this figure for you once again. Let's say this is a thin film, thin parallel film. The film inside has a refractive index of mu. And let's say this is your rarer medium. Above medium is rarer medium. Obviously this will be your denser medium. And this is again rarer medium. Now you can imagine that a light wave is incident here in this wave. This is the normal we have drawn. Let us show the light wave now. Okay, so one ray is incident here at some angle, let's say phi. So a portion of it will be reflected by using the laws of reflection. A part of it will be refracted, and you see it is a denser medium, so it will bend towards the normal. Then again it is transmitted, so it is going in a rarer medium, so it will go away from the normal. Now this ray will also get reflected from this hard surface. It will go there. Okay, and as you can see, it will get transmitted. You can draw a normal here, so it is going to the rarer medium, so it will go away from the normal, parallel, let's say. Then it will get reflected multiple times like this, and each time it will also get transmitted like this. Giving arrow direction is very important. It is coming here, going there. Okay, now just imagine this light ray is going in this direction, so maximum proportion has been reflected. Okay, let's say if 50% is also reflected, the remaining proportion is coming refracted, and some portion is given to the transmitted, some portion reflected, and then it is going. So if you consider the intensity of this light ray and this light ray, there will be a huge difference. Okay, the intensity of this ray, reflected ray 1 and reflected ray 2, there will be a huge difference. And obviously, as it has undergone multiple reflection, its intensity will drastically reduce. So you can imagine, like, it is 100, it is 10, this is 5, and so on. Now main interference will generate due to this two ray. Although you have to consider all the reflected ray to get the proper calculation, but main contribution comes from this two, interference of these two. So you can see we can get interference from two rays. One is this from reflected rays, another from the transmitted rays. Okay. This one, these are reflected rays. One interference pattern we will get from the reflected rays. Another interference pattern we can obtain from the transmitted rays. Let's say the separation between these two parallel film films, or the film thickness, let's say that is T. Film thickness is T. So this is, we are calling it ray 1. This is most important. Interference on the reflected ray, and mainly these two rays, ray 1 and ray 2, are dominating the main interference pattern. Now, as you know that to know the interference intensity, we need to calculate the path difference between these two rays. So let's name this. Let's say this is A. From here, the two rays are generating. A, it is going to B, then it is going to C. Now, if we draw a perpendicular from C to this, let's call this point to be D. So you can see beyond CD, ray 1 and ray 2 are going traveling same distance. So till CD, if we could calculate the path difference, that is the effective path difference. And remember one more thing, that whenever some light ray incident on a rough surface, when it is coming from a rarer to denser medium, so when it is incident on the interface, of a denser medium, it involves a pi phase change. Now, phase difference is 2 pi by lambda times path difference. So effective path difference is lambda by 2 pi times phase difference, that is lambda by 2 pi into pi, that is why it is lambda by 2. So in addition to the path difference originated due to the different distance traveling between ray 1 and ray 2, there will be some additional path difference because of this pi phase change upon the reflection of a hard surface. Remember, here the light ray is falling on the interface. Here also it is falling on the interface of a let's say hard surface, but only this ray 1 will involve pi phase difference. Here also reflection is happening, but here you see it is incident on the interface of the rarer medium. You can see this ray, if I talk about this ray, it is incident on the interface of the rarer medium. Here it is rarer medium, air. So that is why there will be no pi phase change here. But for this light ray, you can see it is incident on denser medium interface. So this will involve a pi phase change. And this ray is transmitted, so there is no question of pi phase change. Do you understand? This is a very important point I am taking. When light ray will go from a rarer medium and will incident on the denser hard surface, it will involve a pi phase change that corresponds to a path change of lambda by 2. Okay. So if I consider the path difference or rather I should write the effective path difference. Effective path difference between ray 1 and ray 2 each, you will see it will be delta is equals to, look, another formula you just note, look, optical, we need to consider optical path difference. Optical path is equals to geometrical path multiplied by the refractive index. when you are moving in air, mu is 1. So that is why geometrical path and optical path are same. That is why in Young's double slit experiment, it did not create any problem. Now we have already, I think, mentioned when we inserted a thin plate, we talked about it, right? So here the light ray is traveling through, you can say ray 2 is traveling through this denser medium or film, but ray 1 is traveling in air. So delta, you can see AB plus BC, this much of distance, geometrical path difference AB plus BC, it is traveled in the film. We need to multiply a mu here. So till this CD, we need to calculate the path difference, mu times AB plus BC. This is the path traveled by ray 2. What is the path traveled by ray 1? It is, before CD, it is AD, right? So AD. Now a factor of lambda by 2 should be added here, because ray 1 is also involving a pi phase change. So plus lambda by 2. And if you calculate mu into AB plus BC minus AD, this value will come out to be twice mu D. Okay, let's call this incident angle, if you call it phi, this angle of refraction will be pi. Okay, now if you just take it in this way, so this angle will automatically become phi prime. This and this distance is same. Or we can, okay, you just understand. So twice mu D cos phi prime. Here we write the angle of refraction minus lambda by 2. Phi prime is the angle of refraction. So this is the path difference for the two rays, ray 1 and ray 2. That is why we get the condition of interference for reflected light, for reflected light. What will be the condition for, let's say, maxima? Obviously this delta is equals to n lambda, or twice mu D cos phi prime minus lambda by 2 is equals to n lambda, and that is why it is twice mu D cos phi prime is equals to n plus half times. So this is the condition of the maxima in an interference, in a thin film interference. From the reflected light. So it is a condition of maxima, but it is like, let's say, looking like n plus half lambda. It is looking like the condition of minima, but it is actually the condition of maxima because of this extra phase difference due to reflection. So this is the condition for maxima, and it is let's say if we write the condition for minima. What is the condition for minima? Delta is equals to n plus half times lambda, we know that. It means twice mu D cos phi prime minus lambda by 2 is equals to n plus half lambda. That is twice mu D cos phi prime is equals to n plus 1 times lambda. And this can be approximated to n lambda. You can imagine it in this way, that light is going in along in this way, and this is the peak to peak separation, this is lambda. So it is a wave train like this. So n plus 1 lambda is meaning n plus 1 such units has been repeated to make up this wave. Now if you just take out one such lambda from the wave, the condition of interference does not change. That is why n plus 1 lambda, we can approximate it to n lambda, and because of that we get our minima condition twice mu d cos phi prime is equals to n lambda. And remember, n will run from 0, 1, 2, 3 and so on. So can you tell me what should be the color of the central fringe? It will be bright or dark? Central fringe would be bright or dark? What about the center, guys? Tell me. Central fringe will be bright or dark? Harry, Ajay, Mulli, tell me. Central fringe will be bright or dark? Dark. Okay, very good. Because n equals to 0, it is satisfying the condition of minima, so that is why it will give you dark. This is for reflected light. Now what will be the condition for this transmitted light? For transmitted light, this will be just opposite. We are not going to do that. We will just write for transmitted light. For transmitted light, you will get the condition of maxima and minima in this way. Condition for maxima. Look, as I told you, it will just be opposite. Twice mu d cos phi prime is equals to n plus half lambda. So for maxima, it will become twice mu d cos phi prime equals to n lambda. So the condition for minima in bright light, in reflected rays, becomes the condition of maxima for transmitted light, and the condition for maxima will be the condition of minima. Okay. So from the transmitted light, you will see the center to be bright, but for the reflected light, you will see the center to be dark. Now this is the interference involving thin films, parallel thin. These are called parallel thin film. Okay, because the film is contained in between two parallel plates, it is called parallel thin film. Now if we make an angle between these two hard surfaces, it will give you wedge shaped film. So for wedge shaped film, there will be a little bit difference. Wedge shaped film, we are not going much into detail of this thing, wedge shaped film, but you just remember that previously we had the parallel thin films. Now here what happens, instead of parallel, we have a constant angle between these two films like this. You can see they are, let's say, being like this. This angle, let's say theta, and it is again filled with film. So this is called wedge shaped film. So what will be the difference for wedge shaped film? The condition for maxima minima will be very similar. Instead of this phi prime in the argument section, so in place of phi prime, it will just be this angle theta will be added. So instead of twice mu d cos phi prime, here also multiple reflections will be there. Here you have to use twice mu d cos phi prime plus the angle of wedge theta. Here fringes of equal thickness will be observed. You will get straight films, straight fringe like this. Bright dark this way. चलो एक प्रॉब्लम करते हैं. लेट्स डू ए प्रॉब्लम. दिस प्रॉब्लम केम इन December 2014. Do it. A parallel beam of light of wavelength lambda is incident normally on a thin polymer film with air on both sides. If the film has a refractive index n greater than 1, the second order bright fringe can be observed in reflection from the reflected light. Second order, when the thickness of the film is n equals to 1, you will take, है ना? Do it quickly. Option C, very good. So for bright fringe, we know the condition twice mu d cos phi prime is equals to n plus half lambda. For second order bright fringe, n is equals to 1, 0 then 1. Therefore, twice mu d, d is the thickness, cos phi prime, so cos 0, because it is normally. For normal incidence, angle of reflection and angle of refraction is 0 degree. C lambda by 4 mu. Here refractive index has been denoted by n. 3 lambda by 4. Chalo. Okay, let's move on to the next question. I hope this is understood. A parallel beam of light of wavelength 5.90 angstrom is incident on a thin glass plate, mu equals to 1.5 given, such that the angle of refraction into the plate is 60 degree. What is the smallest thickness of the glass plate which will appear dark by reflection? Dark by reflection. Smallest thickness means if you take n equals to 0, it will not work. So you have to find out for the smallest thickness, at least you need to go to n equals to 1. Otherwise the thickness will become 0. Right? Look, the smallest thickness for which the glass will be appear by dark by reflection and by dark. So the condition for dark fringe by reflection, not twice mu d cos phi prime is equals to n lambda. So d is equals to n lambda by twice mu cos phi prime. So if you take n equals to 0, then that will not work. So we have to take n for the minimum smallest thickness, we have to take n equals to 1. And 5890 angstrom 10 to the power minus 10 divided by 2 into mu is 1.5 cos phi prime is 60 degree. This will give you 3.926 10 to the power minus 7 meter. So it is 0.3926 micron. Option C. Okay, very good. Okay, let's quickly go for the remaining topic, that is Newton's ring. Newton's ring is another application of division of amplitude. So let's quickly, have you done this practical in your MSc or BSc? I think in your BSc you must have done it. Have any one of you done this practical? Yes, sir, in MSc. Okay, so then you must have you must have seen this kind of concentric bright and dark rings. So this is exactly, you see, we have also done it in, I think I have done it in BSc, as far as I remember, maybe. Anyways, so you can see this arrangement. Newton's ring arrangement consists of this plano convex lens and a thin plate. So this is very thin actually. Air film is there, so it is actually becoming a wedge shaped film, right? Wedge shaped film of varying thickness. Now possible mechanism has been shared here. Sodium lamp, let's say it is emerging from here, it is focused with the help of a convex lens and a glass plate is placed here. So one portion of this light ray will be going like this, another after reflection it will go like this, and you will get an interference pattern. This is the traveling microscope, so with the help of this you see the things, you see the pattern. So if you imagine that if you do not employ this arrangement, if some arbitrary light ray goes from here, you can see it is reflected from this surface and another from this surface of this lens. So you are getting two rays, that is sufficient for interference. Here in this picture it has been discussed, it has been shown in a very beautiful way. So you imagine this light ray is coming in this way. So this is the light ray. So it is reflected from the lower surface of this thin film, lower surface of this lens. So this is one direct reflected light. Another light is reflected from this optical flat surface. So here you can see it is rarer medium, this is denser medium. So it will obviously involve a pi phase change, as I told you. So if a light comes from rarer medium to a denser medium, if it incidents on the interface of the denser medium, it will involve a pi phase change. So this ray and this ray, there will be path difference. Because of the path difference, you will get this interference pattern. They are originating from the same light ray, means having same frequency, means they are coherent. These two lights, these two sources, okay, these two light rays, they are coherent. So Newton's rings are an interference pattern formed by light reflecting between a convex spherical lens and a flat glass surface. This phenomena is characterized by a series of concentric, means having the same center, bright and dark rings. The patterns arises due to the varying thickness of the air film between the lens and the glass plate, which leads to constructive and destructive interference of the Newton's ring occur when monochromatic light reflects between the curved surface of a lens and a flat surface. It is talking about this. Here it is reflected from the curved surface of the lens and from the flat surface, creating interference due to the varying air film thickness. Bright and dark rings are observed in reflected light due to the path difference between rays reflecting off the lens and the glass plate at the center where the lens touches the glass plate. At the center means here at this point, you can see this lens is touching this glass surface. The thickness of the air film is 0, typically resulting in a dark spot due to the phase shift of pi, part difference del lambda by 2, that occurs upon reflection. Okay. So let me just schematically show you what exactly is happening here. So we have this convex lens and an optically flat surface. So if you imagine, look this, although I have shown it a little bit larger, but you imagine the film content here is very thin. The film is contained in this way. It is very thin. Look, let's say one light wave is coming here. So one part of it is getting reflected directly. Noise in this. Now another part will get reflected from this hard surface. Will reflect it and go in this way. This is the original light ray coming and it is going. Part of it is transmitted, then reflected. So just to show the difference, I am showing with double arrow. So this is ray 1 and this is ray 2. This 2 ray is producing the reflected light, and as you can see here, this ray will be emerging, transmitted in this way, and as you can see after reflect, this is another hard surface, so it is reflecting in this way and it will get transmitted. So it's coming like this. So you can imagine it like 1 prime, this is 2. So these are reflected rays and these are transmitted rays. So if I talk about, let's say, the reflected rays, we need to calculate the path difference delta, that is twice mu d cos phi prime plus, let's say the angle is theta, angle of wedge, minus lambda by 2. As you can see, this ray 2 is involving a pi phase change at this. We will get this lambda minus lambda by 2. Okay. Mu is the refractive index of this thin film. Phi prime is the angle of refraction. And theta, angle of wedge, because it is a wave shaped film. Now, if you implement normal incidence, let's say, I have shown you it is coming. You just, if you imagine, it is normal incidence. So for normal incidence, your phi prime is equals to 0. And if you imagine that for a thin shaped film, for a very thin film, thin wedge angle, theta, you can take it 0 approximately. And if you consider the film to be an air film, mu will be equals to 1. And implementing all these things, we can write, therefore, delta is equals to 2d minus lambda by 2. Can you write it? Mu is equals to 1, cos phi prime plus theta cos 0 is 1. So for this central spot, as you can see, what are you getting? For central dark point, d is equals to 0. Now, d is the variable, d is variable thickness. Okay, here you will calculate 1d. This is d, so variable thickness. अच्छा, यहाँ से हम लोगों का जो लाइट था वो गायब हो गया. So for so you can imagine it is minus lambda by 2, so we can take the positive value lambda by 2. Okay. This is the path difference between these two rays. Hence, the condition for bright ring or maxima from reflected rays. What will be the condition? You can imagine it is 2d delta is equals to 2d minus lambda by 2. This should be equals to, it is n lambda. That means 2d is equals to n plus half times lambda, and same condition if you apply for dark ring. Minima from reflected rays. What you get? Delta, that is 2d minus lambda by 2. This would be equals to n plus half lambda. That means 2d is equals to n plus 1 times lambda, which you can approximate to n lambda. Understood? So these are the condition of bright ring and dark ring. Now what is most important in Newton's ring experiment is the diameter of the rings. Okay. Now what will be the diameter of the rings? Another thing guys, for the transmitted rays, this condition will just be reversed. So this will be the condition of dark ring and this will be the condition of reflected. This will be the condition for bright ring. Okay. I'm not, you can write it somewhere. Don't have space here. You can note for transmitted rays, the condition will just be reversed. Okay. Now, once you get the conditions, we can write the diameter of the rings. What will be the diameter of the rings? Okay, let me just show you a picture first. So, from the reflected light, you will get a pattern like this. You can see the central fringe is dark, and you see the bright, dark, bright, dark, bright, dark. In this way it is going. Don't get hypnotized. So, you can see the separation between the rings. It is more here, and it is getting reduced as you go to up to higher rings. So the separation between the rings increases as the order of the rings. The separation between the rings decreases as you increase the order of the rings. Okay, so this is the first order, second order, third order, fourth order, and so on. For transmitted, it is just the opposite. It starts with black, then white, black, white, then it starts with white and black, then white, black, and so on. The spacing between the consecutive fringes decreases with increase in their order. The rings get closer and closer as n increases. N means the order. So these are higher order rings. As n increases, hence the rings are not evenly spaced. Okay. Now the diameter. What are the ring diameter? So this is the diameter of this bright ring. This is the diameter. Okay, radius. Let's say. If I want to calculate the diameters, you can imagine it. This is the diameter of the bright ring. Let's say if you want to calculate, this is the diameter of the dark ring. So in this way, how will you calculate? What is the formula which will govern the diameter of these rings? So for bright rings from reflected light, the diameter of the ring depends on the order of the ring. Order of the ring means the n value and whether it is bright or dark. For bright rings from reflected light, the diameter dn of the nth bright ring will be 4 times 2n plus 1 r lambda by 2 mu. Here 2n plus 1 denotes odd numbers, right? So 4 times 2n plus r lambda by 2 mu is proportional to root over 2n plus 1. So it is varying as the square root of the odd multiple. These are odd multiple, odd integers, you can say. Square root of odd integers. N equals to 0, 1, 2, 3. R is the radius of curvature of the lens. Okay, the lens, plano-convex lens we have used. So R is the radius of curvature. Dark rings from reflected light, the formula is root over. You see 4 r lambda by 2 mu was there. Here it is 4 r lambda by mu. Here it was 2. Here no 2 is there. Here 2n plus 1 what? Here n proportional to any integer. Okay. So for transmitted light, the formula of ring diameter will just be reversed. For transmitted light, the diameter of the bright ring will be dn is equals to root over 4n lambda r by mu, and diameter of the dark ring will be root over 4 into 2n plus 1 r lambda by twice mu. I hope this is clear. Now, with the help of this Newton's ring, we will be able to do many things. First of all, determination of a wavelength of source. If you are given a source, we do not know the wavelength, we can determine the wavelength of the source. So what you can do, you know the diameter of this ring formed from this Newton ring experiment. So you use the light source, whatever light source you use. So let's count, let's take dn and dn plus m be the diameter of the nth and n plus mth dark rings. So imagine, let's say 5th dark ring you see and 15th dark ring you see. So what is the m value? It is 10, 5 to 15. So what we can write, dark ring from reflected light dn square will be how much? Root over 4n lambda r by mu. This was dn, so square of it will be 4n r lambda by mu. Okay, 4n r lambda upon mu, and your dn plus m square will become 4 instead of n, it will be n plus m r lambda upon mu. Okay. Now if you take the separation or this difference between dn plus m whole square minus dn square, it will be 4 m r lambda upon mu. We know the value of mu, which if you use an air film, then mu will be equals to 1. We don't need to worry. Okay, if I took, let's say, air, then mu is equals to 1. And let's say this is glass, this is lens, this is air. For an air film, mu is equals to 1, therefore dn plus m whole square minus dn square is equals to 4 m r lambda. From this we can get the value of lambda, dn plus m whole square minus dn square divided by 4 m r. Is it clear or not? So you see, r is the radius of curvature. For a provided length, you will be easily able to calculate. You will be easily able to measure this r value. Okay. Now you can measure the diameter of the rings. So you will see the rings in this way, right? You will see the ring in this way, in this way, in this way. So you will just measure the ring. Let's say you take fifth ring, okay, fifth ring, and let's say if you take 15th ring, you can easily measure the diameter with the help of this telescope and or whatever instrument you have. And from the difference of the diameter and putting the radius of curvature value, you can easily get the value of the lambda. So in this way, Newton's ring helps to determine unknown wavelength. Clear? आगे बढ़ें. Now, if you are given a very costly liquid, if you have, and you do not know the refractive index, so you cannot do other experiment. Using Newton's ring experiment will require very little amount of let's say that liquid. If you get a rare liquid, very costly liquid, so you can take a drop of that and you can put it into this instead of air film, you can put that thing, and that will with the help of this Newton's ring experiment, you can evaluate the refractive index of that particular very pricely or very costly liquid. So how will you do that? You see, here now we will be discussing determination of refractive index of a liquid. So once again, you will observe nth ring and n plus mth ring. So when there is a liquid in between this convex lens and this thin glass plate, the liquid will have its refractive index mu. So dn square of the liquid, what will be this value? 4n r lambda by mu. So dark ring. dn plus m whole square of the liquid, the 5 and 15th, let's say. This will be 4 times n plus m r lambda by mu. Now once you measure with air, then you measure with liquid. Now for air, if air is the medium between the glass plate and the lens, then you see dn plus m whole square air minus dn square air, what will be this value? As you have calculated from here, 4m lambda r, 4m r lambda. And here you can see dn plus m square liquid minus dn square liquid is equals to 4 m r lambda by mu. Okay. Now if I take this, let's say this is 1, this is 2. If you divide 2 by 1, what you get? You get mu 4m r lambda divided by 4m lambda by mu. So mu is equals to dn plus m whole square in air minus dn square in air divided by dn plus m whole square in liquid minus dn square in liquid. Clear? So what you do? You will first measure the, let's say, fifth diameter of the fifth ring and 15th dark ring, let's say, in presence of air. Now you just fill this air with a drop of that liquid. Then you will measure those same rings diameter, and from this formula you can easily find out the refractive index of that particular liquid, isn't it? Clear? Tell me. Is there any question from this Newton's ring? We are going to solve some problem. If there is no question, do this problem. Suppose the diameter of the 5th and 15th dark rings in Newton's ring experiment be 0.20 centimeter and 0.48 centimeter respectively. What is the wavelength of the sodium light if the radius of curvature of the plano-convex lens is 81 centimeter? Okay. So here what is given? N is equals to 5, n plus m is equals to 15. So m is equals to 10. dn is equals to 0.02 centimeter. dn plus m is equals to 0.48 centimeter. Radius of curvature is 81 centimeter. So what will be the value of lambda? We know the formula. We know the formula of lambda. dn plus m whole square minus dn square by 4mr. dn plus m whole square minus dn square divided by 4mr. Just put the values. It is 0.48 square minus 0.20 square divided by 4 times m is 10 times r. This will come out to be 587.6 nanometer. Option A. Clear? No issue in this question. One last question we'll do, then we'll wrap up the session. We are already late. A plano-convex lens of radius 300 centimeter is placed on an optically flat glass plate and is illuminated by a monochromatic light. The diameter of the 8 dark ring in the transmitter system is 0.72 centimeter. What is the wavelength of light used? So what is given in this question? A plano-convex lens. This is optically flat surface of radius 300 centimeter, means radius of curvature is 300 centimeter. Illuminated by monochromatic. The diameter of the 8th dark ring is in the transmitted system. Okay, in the transmitted system is 0.72 centimeter. So for transmitted system, dark ring condition will be the condition of the bright ring in reflected system. So for the bright ring reflected system, that was the formula 4 into 2n plus 1 r lambda by 2 mu. This was the formula for bright ring in reflected system, but it is transmitted system. So this will become the condition of the dark ring. So from this expression you get r is equals to, sorry, lambda is equals to twice mu dn square divided by 4 into 2n plus 1 times r. So you just need to put the values. Mu is 1 because this is air. Dn square, dn is given to you how much? 8 dark 0.72 centimeter square. 4 into 2 into 8th, so 8 plus 1. Radius of curvature is 300 centimeter, all of them are centimeter. This will give you 5.082 10 to the power minus 5 centimeter. This is 508.2 nanometer. Okay, this will come out to be 10 to the minus 5 or 7. So 5.08 to 10 to the minus 5, this will come in centimeter. Look, 1 nanometer is equals to 10 to the power minus 9 meter. So this is 10 to the power minus 7 centimeter. Yes, so 508.2 nanometer. ठीक है, option D. Clear, guys? So we are stopping here today. I don't have much time to go, so we'll continue. Okay, this is the end of this interference. We'll start diffraction from the next day. Thank you, guys. Thank you very much for joining the session. I hope you find this session useful. Bye bye, take care, see you in the next